Hello, everyone. Welcome to the NVIDIA Jetson AI session. So today we're going to talk about intelligence beyond the cloud, how NVIDIA Jetson enables machine intelligence on the embedded systems. This is Wei from NVIDIA. Co-presenting with me today is Clinton. Clinton is an Edge Impulse ambassador. He also leads the TinyML Kenya community. This is our agenda for today's session. First, I will share the history of NVIDIA. A lot of people probably still think NVIDIA builds GPUs for gamers. I want to help you bust a myth here. Then we will take a look at the NVIDIA Jetson Edge hardware. Here at Edge Impulse Imagine, you must have heard about TinyML many times. AI models used to run on the cloud. However, high connectivity cost, privacy concerns became the barrier to some solutions. Now, TinyML and NVIDIA Jetson are democratizing AI at the low-cost device level. After that, we will move on introducing NVIDIA software solutions that not only accelerates your AI application at the edge, but also bridges the embedded solutions with the cloud. We will walk through some exciting Jetson-powered applications. Then I will hand over to Clinton to dive deep into the Edge Impulse and the Jetson integration. I want to start my presentation with a piece of video here. Somehow I don't see the play button. See here. I tried this early. Apologize for this. This is the I am AI NVIDIA promotion video. Check it out. It's on YouTube. So please feel free to check it out afterwards. So a little bit history about NVIDIA. NVIDIA started its journey with computer graphics back in 1993. At its core, computer graphics is all about simulation, using mathematics and computer science to simulate the interaction of objects, lighting, and material. 2 years after that, NVIDIA launched the first graphics card, which was capable of handling both 2D and 3D rendering, along with audio processing capability. 1999 was a milestone for NVIDIA. That was the year that NVIDIA invented the Graphics Processing Unit, or GPU. It's a single-chip processor with integrated transforming, lighting, and rendering engines. 1999 to 2000 was a very interesting period. Scientists and researchers started using GPUs to accelerate a range of scientific applications. That was the movement called GPGPU, or General Purpose GPU Computing. However, at that time, GPGPU required the use of graphics programming languages like OpenCL to program. Developers had to make their scientific applications look like graphics applications and map them into problems that drew triangles or polygons that significantly limited the accessibility of GPU for scientific topics. NVIDIA realized the potential of bringing the GPU performance to the larger scientific community and modified the GPU to make it fully programmable. Also added high-level programming language support that includes C, C++, Fortran. In 2006, NVIDIA created a CUDA programming model. CUDA stands for Compute Unified Device Architecture. We're going to touch on this topic slightly later. But CUDA and the latest GPU platform bring parallel processing to general purpose computing. This redefined the computing. Now the paths of the high performance computing and AI innovation began to converge. In 2009, AI pioneers realized that GPU chips could run neural networks in parallel. The discovery unlocked new possibilities for neural networks. Taking a neural net with 100 million parameters as an example, traditional processors require several weeks to calculate all the cascading possibilities. With a cluster of GPUs, you can finish everything within one day. Now, NVIDIA GPUs are used in the embedded Jetson family of devices to laptops, workstations, supercomputers, cloud. Every step of your machine learning workflow, from model training to model deployment, can be accelerated by NVIDIA GPUs. We think about NVIDIA GPUs when we talk about model training. Some interesting data points that I can share with you. The latest natural language processing model, GPT-3, has 175 billion parameters. NVIDIA researchers were able to train the model on 1,024 NVIDIA A100 GPUs in just over a month. Traditionally, machine learning models run on the cloud or the server. These are represented by the block on the right side. On top of the GPU, NVIDIA also rolled out Data Processing Unit, or DPU, as a data center solution. But data is generated at the source at a higher and a higher frequency. So in order to process this data closer to its source, machine learning inference is penetrating to the edge devices. I think autonomous driving is a perfect example of this. Our cars have to make a life-critical decision for us in a millions of seconds. We cannot rely on algorithms running on the cloud side to make a decision. Embedded and ultra-low power devices and sensors are capable of running machine learning models as well. TinyML is not something new to our audience here. The remix of two primitive technologies, IoT and AI, unlocked a lot of embedded AI and TinyML applications. As a matter of fact, a lot of developers I have been working with use TinyML in a hybrid mode. They use microcontroller-enabled machine learning for wake-up detection, then transfer the heavier machine learning workload to the Jetson devices for processing. So our focus today is this block here, Jetson family of embedded device. Let's start with the hardware. Jetson family consists of different modules. Each module combines an NVIDIA GPU, ARM CPU with memory, power management, I/O interfaces, connectivity support. These modules are designed to be the brains of your IoT systems. So from the low end to the high end, family includes Jetson Nano, TX2 series, Jetson Xavier NX, and AGX Xavier. Jetson Nano is the smallest and lowest power module in the family. It supports multiple camera and sensor interfaces, and it's powerful enough to run machine learning networks like MobileNet, ResNet for image classification or segmentation type of use cases. Jetson TX2 series expanded on the capabilities of Nano, makes it a perfect choice for robots, drones, intelligent cameras. Jetson Xavier NX is one of the latest members to the family. Its form factor is the same as the Nano, but it's a much more powerful module. It's capable of running multiple neural networks. It even supports modern complex models with different sensor resolutions, or natural language processing models like BERT-based, BERT-large. And finally, we have the Jetson AGX Xavier series that provides the highest level of performance and can power up autonomous systems. Here I included the full specs of the Jetson family of modules. I only want to draw your attention to the GPU specs. The GPU specs on the Jetson modules result in different performance and different applications. As you can see here, Jetson Nano uses 128-core Maxwell. TX2 uses a 256-core Pascal. These are CUDA GPU cores. CUDA core is analogous to a CPU core. The primary difference is CUDA core is less sophisticated, but implemented in much greater numbers. Xavier NX and ATX Xavier series use Volta architecture-based GPU that includes tensor cores. Essentially, tensor cores are the processing units that accelerate the process of matrix multiplication, which is the basis of the heavy workload deep learning. CUDA cores perform one operation per clock cycle, versus tensor cores can perform multiple operations per cycle. So tensor cores compute a lot faster than the CUDA cores. From the full specs here, you can see with the built-in codec multimedia interfaces, customers can easily deploy AI applications with Jetson. Here I included a chart to give you an apple-to-apple comparison of running different machine learning models on top of Jetson Nano devices versus Raspberry Pi 4. Both devices have 2 gig RAM. So here we included some popular image classification models like Inception 3, MobileNet. I have to say across board, you will be able to observe 2 to 3 times performance enhancement when you run these models on Nano device. So Jetson Nano is a very popular platform for edge AI. Why? It's small, it's portable. It's a small all-in-one computer that you can use to develop different edge AI applications. So the hardware itself, it's of low cost. Dev kit only costs $59. Extremely powerful for edge AI applications. And also because it's part of the NVIDIA ecosystem, you can leverage NVIDIA partners to for a full end-to-end machine learning workflow story. Now let's move on to talk about Jetson Software. Keep this software diagram in mind. This is the cornerstone of Jetson Stack. We will use this diagram to guide through the next few slides. Jetson is supported by the Jetpack SDK, which includes the board support package, BSP, the Linux operating system, support for real-time OS, CUDA, and compatibility with third-party platforms like Robot Operating System or ROS. It also comes with libraries for deep learning, computer vision, accelerated computing, also drivers for a wide range of sensors. Deepstream and Exact SDKs enable developers to quickly build and deploy efficient video analytics and robotics applications. NVIDIA also offers a rich set of developer tools to help you accelerate your application development, debugging, profiling. The foundation of the Jetson software stack is CUDA. So if you have heard about NVIDIA GPUs, you must have heard about CUDA. As mentioned earlier, CUDA is a parallel computing platform and a programming model that makes using a GPU for general purpose computing a lot easier. CUDA is not a programming language or a set of APIs. The developers still need to program in C, C++, Fortran, the languages they're already familiar with. NVIDIA is also adding CUDA support to Python. So the extension of these languages are in the form of a few basic keywords. With the CUDA compiler any piece of code can run on the GPU with the scope of the keyword. It's extremely straightforward to offload computation-intensive tasks from the CPU to the GPU using CUDA. Once the computation is done, the results can be synchronized and pushed back to the CPU side. Well, there are certainly other APIs for GPU development. For example, OpenCL we talked about. And there are other GPU vendors, but the combination of CUDA and NVIDIA GPUs dominates several application categories, including deep learning. One level up in the Jetson software stack are the libraries for deep learning accelerated computing. I will only talk about TensorRT. TensorRT includes an optimizer and a runtime engine. It's the library for machine learning inference acceleration on NVIDIA GPUs. TensorRT optimizer uses different techniques to help you optimize your machine learning graph. Some of the techniques included here, like weight and activation per session collaboration. So, models are trained in floating point 32 full per session. By quantizing them to inter-8 while minimize accuracy loss, TensorRT roughly triples the inference performance of the model. Some other techniques include layer fusion. This layer fusion basically combines successive nodes into one single node for execution. It's like if you need to purchase 3 items from the grocery store, you don't need to visit the store 3 times. You simply purchase all items in one trip. So layer fusion significantly improves the GPU utilization and also optimizes memory storage. So the other part of TensorRT is the converter, the runtime engine. Runtime engine provides parsers for different frameworks. So it doesn't matter if you train your machine learning model with TensorFlow, PyTorch, or PaddlePaddle. The engine can help you convert your graph to the target GPUs, including the GPUs on Jetson family of devices. So for developers, you can use C++ or Python to program. So later on, when Clinton talked about Edge Impulse 2 integration with NVIDIA Jetson, I think Edge Impulse integrated TensorRT into their software stack for acceleration on Jetson family of devices. Now moving up to the application layer. Out of all the AI applications, computer vision-based AI application is one of the most popular category. This is because the avalanche amount of data we are collecting from the CCTV IP cameras operating around us. Also, the latest advancement in the intelligent video analytics led to a surge of new AI applications in smart cities, healthcare, manufacturing. NVIDIA offers Deep Stream SDK that includes a complete streaming analytics toolkit for AI-based multiple video and image processing applications. So here I'm going to use an Agitech use case. This particular use case is built upon NVIDIA Jetson and Deep Stream SDK. Researchers from Blue River Technology, which is now part of John Deere, discovered that a very common problem in modern agriculture is the overuse of herbicides and weed control. Current broadcast spray method delivers the same amount of herbicides to each plant. Also, weeds compete for water, nutrients, sunlight, and space. And weeds are becoming more and more herbicide resistant. So the company developed a see and spray machine using computer vision and machine learning to detect, identify, and make real-time decisions about each plant in the field. NVIDIA Jetson-powered smart cameras are mounted to the tractor to identify crops and weeds and trigger precisely metered sprays. They use DeepStream SDK to build their video analytics solution. This particular See and Spray solution was able to reduce the herbicide use by 90%. The other Jetson SDK is called Jetpack SDK. This is developed for intelligent robot applications. The SDK includes the Jetpack engine, which is basically an application framework, packages for high-performance robotics algorithms, reference applications, and also a very powerful simulation platform. The tools and the APIs packaged as part of the Jetpack SDK accelerate robot development. On the right side, you can see the screenshot here. CUDA is provided as part of the reference app in the Jetpack SDK. Cool. So we touched on CUDA TensorRT application development. There is one thing we need to worry about, which is deployment. Model deployment is definitely not an easy task. Across the spectrum, developers face very different challenges, including diverse software frameworks and inference requirements, hardware complexity and utilization, and also scalable machine learning model serving and orchestration. So for data scientists and application developers, your primary challenge is the diverse software framework and inference requirement. Data science today use a variety of frameworks to train their models, which includes, TensorRT, PyTorch. However, normally serving applications normally only support one of these frameworks. So developers have to convert the models between different formats or use different inference applications to serve different models. In the meantime, applications have independent inference requirements. Some require real-time inferencing, some require batch processing to maximize throughput. For developers, for embedded developers or SoC developers, your primary challenge is the increasing hardware complexity and hardware resource underutilization. So starting from hardware complexity, we now run machine learning inference on CPU, GPU, NPU. How could we use one single serving application that gets the best inference mileage out of the disparate hardware architectures? The second aspect of the challenge here is the hardware utilization. In deep learning applications, inference drives as much as 90% of the compute costs of the application. Accelerated computing power is often oversized. The third challenge here is related to DevOps, how to scale machine learning model serving and orchestration. So when we talk about these challenges, inference serving comes into the picture. There are different machine learning inference serving tools on the market. Popular ones include Google TensorFlow Serving, Facebook Torch Serve, KF Serving. Usually these tools only support one machine learning framework or specific hardware infrastructure. NVIDIA started an open source project called Triton Inference Server a few years ago to address the challenges we just talked about. Triton adopts a client-server architecture. Triton client sends inference request to the server, which pulls the machine learning models from the model repo and sends the inference results back to the client. Programming interface between client-server can be HTTP or gRPC. Triton Inference Server also supports CPUs and GPUs. You can also integrate it with Kubernetes in order to scale up and scale out. To increase hardware utilization, Triton also supports dynamic batching and concurrent model execution, which means you can run multiple copies of a model or multiple machine learning models in parallel. For forward compatibility, Triton also uses a concept called Backhand. TensorFlow, PyTorch, and TensorRT we just introduced can be configured as Triton backend. And you can also develop your own backend for hardware and framework extension. Triton has been widely used by companies including Microsoft Azure, Google Cloud Service, American Express. And specifically for Jetson developers, now we offer Triton for embedded device, which means you can run the software stack on devices like NXP MX, Raspberry Pi, Jetson, and use the single software stack to serve your application across different platforms. For acceleration, you can just configure different backends in order to get the best performance. Cool. Development, Jetpack SDK. Given the time we have, I will not dive deep into this. Later on, Clinton will talk about how you can use Edge Impulse tool to develop for Jetson devices. I want to share some Jetson applications. Jetson has a very vibrant community. Like Raspberry Pi and Arduino, our community members have been contributing to the proliferation of Jetson-based AI applications. I'm pretty sure you will be inspired by your fellow developers. So a couple of use cases. I want to start with a smart city use case. Verizon has been driving future smart city initiative. In this solution here, Jetson-powered smart camera arrays are mounted to streetlights. The arrays use Jetson deep learning capability to analyze multiple streams of video data in order to improve traffic flow, pedestrian safety, and also optimize parking in urban areas. So on the Jetson hardware, it runs Jetpack SDK, TensorRT inference engine, and the DeepStream SDK. They help the developers unlock the full potentials on the device. The solution has been deployed to a couple of cities in California and Massachusetts. Now moving on to the manufacturing floor. We all know Foxconn, a Taiwan-based technology group who produces 40% of the consumer electronics sold worldwide. And they are rising to the opportunity to deliver impeccable quality assurance by deploying AI inspection systems. So Foxconn use UNet machine learning model running on Jetson TX2 devices for visual inspection. And with this solution, the defect escape rate was able to drop to 0.015%. So Jetson-powered robot solutions are not only used in shopping malls and for logistics, they're being used in the most challenging environments, including satellite or under the ocean. One of our Jetson customer, Roboco, developed this marine robot for subsea survey based on 3D computer vision and AI data analysis. Because of the high performance video encoders and the powerful GPUs running on the device, ocean insights can be generated real time on the device. So last but not least, another use case I want to share with you. Let's move to life science. Genomic sequencing is the process of identifying the DNA sequencing of anything biological, including animal, food, water, air. It's a very important step towards better scientific understanding. This device here is called Minion. It's a rapid analysis device powered by TX2, Jetson TX2 module. It provides real-time high-throughput data analysis. Because it's portable, scientists can use it at any location to test crops, animals, drinking water for early detection and prevention of disease. It helps draw immediate diagnosis of a devastating plant disease in Africa, and can also be used for onset testing for viruses such as Zika. So I hope I give you an overview of what NVIDIA offers. Here is a quick recap. On top of the GPU hardware, we create systems, libraries, and developer SDKs for your full end-to-end machine learning journey. And if you want to learn more about NVIDIA technology and Jetson, join NVIDIA Developer Program. Everything is accessible online. We also have a Deep Learning Institute, provides courses on Jetson and different SDKs. NVIDIA's anchor event, NvidiaGTC, will take place on between November 8th to 11th. We curated 500 technical sessions for our audience, so you're more than welcome to join us. Thank you. Clinton, I'm going to hand over to you.
Thank you, for the interesting presentation. So for my session, it's going to be a demo session. And first of all, before we do a demo, I'm going to take you through Edge Impulse platform and how you can use the Edge Impulse platform to train models that run on Jetson Nano. So I'll just share my screen. So Edge Impulse is an embedded ML development platform free for developers. So what you can do with them, Edge Impulse, is that you can collect datasets, build models, test them, and deploy them and test them for deployment. So with Edge Impulse, you can train computer vision models that involves object detection models and image classification models. You can also train and test sound recognition models, anomaly detection models, and also motion recognition models. So since today's conversation is all about NVIDIA and Edge Impulse supports Jetson devices through the TensorRT library, whereby you can utilize the Edge Impulse Studio to build models with support of TensorRT to leverage full GPU acceleration for the Jetson Nano. Edge Impulse also has Linus SDK that can enable developers to do other tasks such as easily build their own custom application for inferencing. That is the case whereby, for example, you have built a model and it's detecting something and you want the notification to reach to somebody else. So Edge Impulse Linux SDK enables all developers to quickly and easily build this custom application. It also enables developers to collect data, new sensor data for training the ML applications. The available SDKs includes Python, Node.js, C++, and Go. One of the cool things about Edge Impulse is the EON Tuna feature. So the EON Tuna is an AutoML feature that enables developers to get the best combination between DSP block and ML block for the application. This is the case of sound recognition models. And one interesting thing that was announced at Edge Impulse Imagine keynote yesterday was that EON Tuna can today also support computer vision models and also motion recognition models. So initially it used to support only sound recognition models, but from today it's going to allow for support for computer vision models and also motion recognition models. So today we are going to do a demo, and the demo will be all about detecting illegal logging in the forest. As you know, the rate of illegal logging has really increased, and we really need solutions that can enable us detect illegal logging at an early stage without really depending on streaming the audio data to the cloud. So EdgeML is the best solution for this particular case. And for this particular demo, we are going to deal with a sound recognition problem, whereby you're going to detect chainsaw audio from the forest. As you know, forest usually has a lot of sounds, just the background sounds which usually include like waterfalls, sound of waterfalls, sounds of a lot of birds and animals, and also some trucks that may pass by, which may be carrying like the logs that has been cut illegally. So I'm just going to share my screen. Studio. So this is the Edge Impulse Studio. So immediately you log into your Edge Impulse account, you're going to create a project, and this is the first page that's going to appear. So when you look at the left side, it shows you all functionalities that you can leverage using the platform to build your embedded ML projects. So if you look, the first thing you can see is devices. Device actually involves like devices that has been connected to your platform. These are devices that you can be using for deployment, or also devices that you may want to use to collect your sensor data that you may want to train with, you may want to use to train your ML models. So the second thing is the data acquisition part. There are very many ways that you can use Edge Impulse platform to bring your data to the platform. The first one is using Uploader, whereby you just upload the data that you already have. The second one is using the device that you have connected to the Edge Impulse platform, whereby you collect the sensor data in real time. So for this case, since it's an illegal logging problem, we are going to have like 3 classes of data. The first one is chainsaw, the second one is tracks, and the other one is noise. For this case, noise is all other noise from in the forest. So as you can see, the data has been split into 2, the training set and the test set, at a ratio of 81% for the train set and 19% for the test set. So the next thing will be automatically to create a model. And there are 2 options of creating models today using Edge Impulse platform. You can use the normal way, whereby you're going to use like the original method of creating models, whereby it's not an AutoML, whereby everything has been done for you. You define everything in that. You define every step during the process. So for our case, we are dealing with for this demo, we are going to do we are going to go that way. But the other method is using like the EON Tuna, whereby the EON Tuna like does everything for you. You just feed your data and give it like a specification of your target device and everything that you may want, including things like latency and also like a compute that you have, so that the model that is trained can be fit for that specific use case that you want. So for us, we are not going to do that because it usually take a lot of time, because it needs to do a lot of search between like the best DSP models. For maybe if it's an audio problem, it's going to decide whether the best combination will be MFCC and a neural network, or spectrogram and neural network. So Edge Impulse EON Tuna usually does all that. So for our case, we are just going to go directly here, and we are dealing with time series data, audio time series data. So with a window size of 100 milliseconds, 1,000 milliseconds, which is typically 1 minute, and 1 second, I mean. And we are going to use a window size of 500, but you can reduce it to 100. Then a frequency of 16,000 megahertz. Then we are going to add our DSP block. So like here you can choose any DSP block that you may think that it's going to perform well for your custom application. But here, since we are dealing with sound data, it will be better if we use MFCC or spectrogram. And they usually that notion whereby if you're dealing with sound data, it's usually better if you use MFCCs, and when you're dealing with voice data, it's usually better if you use MFCC. But if you're dealing with non-voice data, spectrogram is always the best fit. So for our case, we're going to choose spectrogram for this case, but you can also try MFCC to see the performance and compare. Then we are going to add a learning block, which is a classification block. Then we have three output features, which are chainsaw, tracks, and noise. So we are going to save the impulse. Then we are going to come now to our spectrogram. So here, we're just going to click to save the parameters. Then you're going to generate the features. The good thing about the generated features, it can enable you to know how your data separates even before training the ML model. So typical, even without doing machine learning, just using the features generated using a digital signal processing technique that you have chosen, you can easily know how your data is going to separate using the feature explorer. So for our case here, the features are generating, and you can see the progress of how everything is going. So what will happen is that in this section here of the feature explorer, you're going to be given a 3-dimension block of how the data separates just using the extracted features. So you just need to wait a little. And you can see the job was completed. So as you can see, here is our data. You can see the data separates, but not that quite well. Just using the DSP, the processed features, the data already separates, but not that much. Now this is the point whereby now we are going to create our neural network classifier, which is going to help us find the line of best fit to separate the data, which is not necessarily a straight line, but just a line that can separate all those. So for this case, you can just leave everything default, but since we don't have much time here, we can't train with 100 epochs, we're going to do with 10 instead. And we're going to start training. So what's happening here is that now the neural network that we have defined in the neural classifier here, what's going to do is that it's now going to find the line of best fit between the features that have been extracted from the audio data using this spectrogram here that we created in this section of edging the impulse design. So the job has already started. You can just give it around a minute or two to train for 10 epochs. So as it trained, maybe we can talk about other things. For example, here is the EON Tuna. This is the other alternative for training a model. This is usually the case maybe whereby you don't know the best combination between the feature extractors that you want to use and the type of neural network. So the EON Tuna usually comes in handy because it's an automel that does all that for you. All you need to do is just to fit in the data and start, and with the specification of the model that you want. This includes like the amount of compute that you have at that particular time, and also like the amount of accuracy, let's say, that you may also want. So then that's the EON Tuna. It's usually better if you compare it with this other method, because this other method usually based on trial and error. You need to try a lot of things. So for example, for now we have used like the spectrogram. Next time it means that maybe you're going to start try for MFCC. If you do that for very many features, you realize that it takes a lot of time. So, and that's where the EON Tuna usually comes in. The EON Tuna usually enables you to do all that work with just one click of button here. So our model seems it has completed training. Yeah, and if we look at the performance, the model currently has an accuracy of 100%. Maybe this may be, maybe the model may have overfit. So like it may be a problem with the data, maybe because like this is usually the case, but 100% accuracy is a good thing, considering that you're using a tool that you don't need like you don't need a lot of data science knowledge to do that. So that's a good performance. And if you can see like the feature explorer, this is how the model performed in different cases. And if you look at the on-device performance, the model will run at 25 milliseconds, and for inferencing, and use a peak RAM of 16 KBs and a flash usage of 35 KBs. So if you feel that you're not satisfied with the model's performance, let's say like the accuracy of the model wasn't like wasn't what you wanted, you may again try and retrain the model. Now this time you may want to use like a different processing block, and maybe you try like a different neural network architecture. So another thing that you can do with Edge Impulse Studio is live classification, whereby you can test the model's performance live using like the devices that you have connected, the devices that you have connected at the studio to. So another thing, you can do model testing, which really gives you like an indication of how your model is performing. So maybe we can just do this. So we're going to classify all and see how it performs. And as you can see, the model also performs very well when testing with the data that it has never seen, because this is the data that we had splitted when we were this data that we're using for testing is the 19% that we had splitted when we were importing our data. So the model performs quite well. So maybe it's if it could have been something less than 100 or something very less, let's say 60 and below, maybe we may have concluded that our model could have overfitted, since like it gave us a validation accuracy of 100% during training. So when it comes to deployment, even before you go to deployment, there is versioning, where you can basically version your task or your models. So maybe you want that to be the first version, and you maybe want to try other things with other configuration. You can take that as another version. So on the deployment part, you'll find a lot of boards, development boards that you can use to deploy your models onto, straightforward. So you can either deploy them as a libraries or a firmware, flashing firmware directly. So these are the available boards that you can currently use to deploy edge impulse models directly using the studio. So for our case, since we'll be using like a since we'll be using like the Jetson Nano, we use like the TensorRT library. So what we'll do is just select TensorRT library and build it. You can see it's still building. Yeah, and our model has finished. So what you'll do is you'll just save it and use it on your Jetson Nano. So this is a very easy way of creating, of building embedded ML application, rather than like going the conventional way, whereby you really need to write like a lot of code. So this graphical user interface platform, a GUI platform that can reduce all the complexities in the embedded ML development cycle. Yeah. So another way you can use to test your model using the platform is you can use the Edge Impulse Linux SDK, whereby you can, let me share my screen again. Yeah, you can just go to your Jetson Nano when you want to test the model, or you want to deploy now the model after building. So what you can do, you can just follow this guide. It's in the Edge Impulse docs part. So what you need to do is you just need to follow these 3 simple steps. So the first one, you just need to set up your NVIDIA Jetson Nano. You can use like the NVIDIA setup instructions on the NVIDIA platform. Then the next thing you need to do is to install the dependencies, and the dependencies are, you're going to do that using only one command. So what you're going to do is that you're just going to run this command here on your terminal on the Jetson Nano, and it's going to download and install all the dependencies. Then you're going to connect to Edge Impulse Studio using this command, Edge Impulse Linux. Then you will immediately see the board on your studio. Then after that, when it comes to deployment, you can just use this command here, edge impulse Linux runner, to deploy now, to run the model that you have built on the Jetson Nano. And that's basically all of it for today on how you can leverage the Edge Impulse Studio to create models for Jetson Nano. Thank you. You're going to take questions. Wait.
Sure. Any questions from our audience? We still have a couple of minutes here. Thank you, Clinton. This is a fantastic presentation. I learned something new myself.
Great.
Okay, so it looks like we don't have any further questions from our audience. So in that case, I think we can wrap up here. If you have any questions, check out Edge Impulse website. Edge Impulse has a very active developer forum. And if you run into any hurdles during your implementation, please raise your questions there. Also check out the NVIDIA developer portal. You will find a lot of documentations there as well. Yeah, I think there is a question, is GoGLAN officially supported for development on Edge Impulse and the Jetson Nano? I actually don't know about this one. Clinton, do you have any insights?
Yeah, sure. I have an insight on that. So these are the currently available SDKs that are Edge Impulse support for Linux. So we have Python, we have Node.js, we have C++, and we have Go. Yeah, these are the available SDKs. I hope that answered the question. Great.
Wonderful. Cool. Yeah, we will share our presentation decks afterwards.
Sure.
Yeah. Okay, if there are no further questions from our audience today, we will wrap up here. Thank you very much for your time. We hope you find this exciting. Thank you.